SwayamPrabha. Digital India. Educated India.
In this lecture, let us complete our discussion on compressible boundary layer equations with an emphasis on aerodynamic heating and drag. We will look at velocity and temperature distribution within laminar compressible boundary layer for flat plate, both by using adiabatic and isothermal walls. We will look at aerodynamic heating due to viscous effects, and we will look at compressible laminar boundary layer equations for stagnation point flow, which is very relevant for the blunt shaped noses of some of the high Mach number vehicles. In the earlier lecture, as you may recall, we were looking at the CF values for both compressible boundary layer as well as incompressible boundary layer over a flat plate, and we were trying to compare the relations. And we also looked at the heat transfer coefficients and looked at the similarities and dissimilarities. We briefly talked about the Reynolds analogy, which exists between the CF and CH as a connection. We continue that discussion, and we now look at some of the numerical solutions. Here we are showing two plots which were first reported in a work by Van Driest, who is a very big name in this domain of compressible boundary layer theory for flat plate, and it came as long back as 1952, which is nearly 8 years back, where one of the first reported numerical calculations of the boundary layer profiles was available. And we begin the discussion by looking at the velocity profiles. The following results are based on a Prandtl number value of 0.75, and we have used the Sutherland's law for mu. That was what was used by Van Driest in his work, and the velocity profiles are available for two different boundary conditions, an adiabatic wall and isothermal wall respectively. And the adiabatic wall is basically a thermally insulated wall, where the velocity profiles, as you can very nicely see over here, take up much higher boundary layer thicknesses the dimension that we have shown over here, as you can see, this is a non-dimensional value, this is also a non-dimensional parameter. It is some kind of a representation of eta that we have in the y axis, and u by ue is basically the value that we are representing along the x axis, and obviously u by ue stretches from 0 to 1, while y by x times under root rex stretches from 0 to large values, which are not necessarily confined to any limiting value. Interestingly, you find that the adiabatic wall values for a free stream Mach number of 20 go up as high as 60 or beyond, while for isothermal wall condition, where the wall temperature is 25% of the free stream static temperature, spans only up to a value of about 30 for the same free stream Mach number, which is a clear indication of two things. One is that in general the adiabatic boundary layer thicknesses are larger than the isothermal boundary layer thicknesses, especially when the wall temperatures are low, which is indicated over here through a ratio of T wall by T e less than 1. Again, as the Mach number increases, the boundary layer thicknesses grow quite rapidly, and if you were to compare the results with respect to the incompressible result, where m infinity is equal to 0, the thicknesses are way larger than them. So, these are some of the things one can conclude by looking at these plots. So, for both adiabatic wall and isothermal wall, boundary layer thickness increases rapidly with increase in Mach number, and the laminar boundary layer thickness actually varies as m infinity square or m e square, whichever way you call it, and therefore, there is a rapid rise with increase in Mach number. When it comes to isothermal wall, when the T wall is less than the adiabatic wall temperature, then we say it is a cold wall, while when it is larger, we say it is a hot wall. So, T adiabatic wall, which is basically the equilibrium temperature, is basically the basis for comparison. In a cold wall, heat flows into the wall from the flow. In a hot wall, the heat flows from the wall into the flow field. Effect of a cold wall is to reduce the boundary layer thickness. Now, as T w by T e ratio becomes smaller, obviously the boundary layer thickness reduces. We already got an indication in the previous slides plot over here. And if the boundary layer thickness reduces, consequently f double dash becomes larger, since the velocity gradient at the wall becomes larger. It is like saying that you have two situations, one here, another over here, which are caused purely because of difference in the wall temperature ratio. Say for this one it is a certain value K 1, while for the other one it is K 2, where obviously K 1 is less than K 2. Then the velocity profiles may look like this. So, here you need to understand that we are not talking about showing the velocity profiles at two different streamwise locations, but it is for the first and the second case. And since it is a self similar solution anyway, it does not have any dependence on the streamwise station. So, these are distinct cases, but the only basis for comparison is that the u is identical for the two cases. If that is the situation, then you will clearly see that in a case 1, the del u by del y at the wall for case 1 is obviously going to be greater than del u del y at the wall. So, you need to make a small correction here. It is not equal to 0, rather we are just talking about what that value is and comparing it with case 2. So, naturally the gradients compare like this, and that is basically the effect of reduction of the boundary layer thickness. As a consequence, if the boundary layer thickness reduces and the f double dash becomes larger, you will have Cf root Rex becoming larger for the entire Mach number range and vice versa. We will see what is the implication of that. So, here along the y axis we are plotting Cf under root Rex, along the x axis we are plotting m infinity or m e, and the Mach number range goes from 0 to 20, and the Cf range weighted by under root Rex goes as high as 0.7 starting from 0.2, and you have a number of plots over here for different wall boundary conditions. So, you see that you have the lower values of T w T e curves at the highest levels, and as the TW by TE increases, the curve goes lower, and they tend to asymptotically move very close to each other as the Mach number grows. At Mach 20 they have got very close to each other, but at the lower Mach numbers they are more stretched apart from each other. And here comes the adiabatic wall distribution. And an interesting point to note over here is the point 664, which has a particular relevance. It is basically the incompressible flow result. As m infinity tends to 0, the Cf into root Rex will be tending towards 0.664, which we have discussed earlier also from the Blasius solution. So, this basically gives you the flat plate skin friction coefficient for both isothermal wall and adiabatic wall cases. This is a very important and interesting distribution. Again, remember that we talked about Reynolds analogy, and from that we can infer that the Ch root Rex distribution would be somewhat analogous to this. Cf decreases as m infinity increases, both for isothermal and adiabatic wall. However, we should not be misled that that also drives the dimensional values, because if you look at the wall shear stress, then how does it depend on Cf? It depends on half rho u e square times Cf. In terms of Mach number, it is how this is how you represent it. So, this is a form which we more often use for compressible flows, half gamma P e m e square times Cf, and it clearly shows the quadratic dependence of tau w on m e. Therefore, as m e increases, the tau w will dramatically increase, and even though that at the higher Mach numbers there is a reduction in Cf, but that reduction is not going to offset the increase of tau w much, because you need to note the values over here. It is only decreasing by about half, by a factor of half, while the m e square values are very large. So, that reduction won't matter so much anyway. Therefore, at higher Mach numbers there will be a prohibitive increase in drag. Therefore, to reduce the prohibitive drag, the vehicles which are like hypersonic cruise kind of vehicles, they could fly at high Mach numbers only at high altitudes where the pressure and density are much lower than near sea level conditions. The trends shown in Ch under root Rex versus Mach number would be very similar, as we already mentioned, due to the Reynolds analogy. Again, interestingly and very conveniently, the incompressible flow result that Cf by 2 Ch is equal to Prandtl number raised to the power of 2/3 is valid for compressible boundary layers too, and there is only about a 2% variation over a large range of Mach number from 0 to 16, which basically means that the Cf under root Rex versus Mach number plot can be used to obtain the Ch value too, and with reasonably good precision. Now, coming to the temperature profiles for the adiabatic wall and the isothermal wall again, and with the same wall to free stream temperature ratio. These are very interesting plots where you see again that as the Mach number increases, how the temperature distributions change. Again, you have an indication of eta along the y direction in terms of y by x times under root Rex, and you see interestingly that in the adiabatic wall, as the temperature approaches the wall, it of course, this would be in terms of dt d eta, because here we are talking about ordinary derivatives, and therefore, you can call it T dash that approaches a value of 0 as you move close to the wall, while in the case of the isothermal wall, there is a peak value of the temperature being represented in the ratio form with respect to the free stream temperature, and this peak value becomes larger and larger as the Mach number increases. So, starting from the much lower values at Mach numbers of this order, by the time you reach a Mach 20 situation, there is a manifold increase in the temperature that you see within the boundary layer, and therefore, this is prone to triggering chemical reactions within the boundary layer. However, in the analysis that we are doing presently, we do not account for those effects. We look at all these effects in the later part of the course. Similar things are going to happen in this case to a much greater extent. In fact, if you look at the scales over here, at Mach 20, the T by TE maximum value is around 16 or so, while here we are talking about as high as 70 at the wall. Therefore, adiabatic wall definitely creates much larger temperatures. So, like for the hydrodynamic boundary layer, where we looked at the velocity distribution for both adiabatic wall and isothermal wall, the thermal boundary layer that we looked at, which basically means the region adjacent to the wall where temperature variations take place, the thermal boundary layer thickness increases with increase in m infinity, and we can show that the thermal boundary layer thickness scales with the hydrodynamic boundary layer thickness too through the Prandtl number. The temperature levels within the thermal boundary layer for the cold wall case are considerably lower than in the adiabatic wall case. So, there should be a layer word added here. Considering identical pressure for both the cases, if you invoke the equation of state P equal to rho RT, then the outcome is that the density in the cold wall case is much higher. Since density is higher, the mass flow within the boundary layer can be accommodated within a smaller boundary layer thickness. Therefore, the thin boundary layers that we see for a cold wall case. Now, the cold wall case also means the temperature peaks in some region of the boundary layer, and the higher the temperature peak, higher is the viscous dissipation occurring within the boundary layer, and that is basically why the peak is growing stronger. Viscous dissipation is the cause, the temperature peak or the enthalpy peak is basically the effect. Higher the temperature peak, higher is the QW at the wall, which means the heat transfer that occurs at the wall, because that keeps increasing the temperature or the enthalpy derivative at the wall, which is responsible for the higher heat transfer coefficient. Focusing a little further on aerodynamic heating, let us look at the Stanton number expression once more, and let us try to develop some intuitive sense, some more engineering sense from this equation, where even without going for a very elaborate solution of the ODEs based on the boundary conditions and so on, we can still get some empirical relations which are to a good extent accurate, and that is of enormous engineering significance. Now, in this equation, the difference between the adiabatic wall temperature and the actual wall temperature, though here it is in terms of enthalpy. So, you might as well call it as the enthalpy difference in the present equation. So, that is called as the driving potential. This needs to be obtained in engineering related calculations, where detailed solution of the ODEs with the adiabatic wall condition may not be available readily, but you need to make an estimate impromptu very quickly. Now, how do you go about doing that? The value of the enthalpy for the adiabatic wall can be expressed in terms of a recovery factor, and which is very important for engineering estimates. It is basically the fraction of the specific kinetic energy available in the free stream which gets converted to the enthalpy at the wall. So, it is the one which is available in the free stream and how far is it getting converted to enthalpy at the wall, that is governed by the recovery factor. and this is applicable for the adiabatic wall condition case. So, when you plug in the recovery factor, it basically gets clubbed with the free stream kinetic energy in a specific sense. So, you see that R is going to play a role in determining what the adiabatic wall enthalpy level will be, and the stagnation enthalpy is of course the driving factor that is given by this relation in terms of static enthalpy and the kinetic head. And if you compare the two equations, you see this is how they get together, and then if you rearrange that equation, you get a definition for the recovery factor in terms of the enthalpies at the free stream, in terms of the stagnation sense as well as static sense, and the adiabatic wall enthalpy level. For a calorically perfect gas, since Cp is constant, it can also be expressed in the temperature ratio sense. Now, for incompressible flow, we know that the recovery factor is under root Prandtl number, and here too we have a good fortune that the value decreases only by about 2.4% when we increase the Mach number from 0, that is for incompressible case, to as high as 16 or so, which means it works both for supersonic as well as hypersonic regimes, and this is a very convenient finding that we might as well go ahead with R equal to under root Prandtl number even for this higher Mach number ranges. And when you plug it in, you find that the adiabatic wall enthalpy level will be in terms of H E under root Prandtl number and the difference between H naught and H E. So, this can be plugged into the QW expression subsequently, so that you are able to get to a point where you express the aerodynamic heating in terms of the driving potential, Stanton number, and the rho E U E product. If we take a value of Prandtl number equal to 0.71, which works for air over a wide range of temperatures, then the under root Prandtl number, which is important for us from the recovery factor point of view, is 0.84, which in terms of engineering estimates is order 1 quantity. Therefore, the HAW can be approximately written as H naught, where H naught is given by this relation, and we are making an order of estimate analysis here. So, approximations work to a good extent. Again, at hypersonic speeds, the UE square which figures over here is much larger than HE, the free stream static enthalpy, because the dynamic enthalpy is going to be very large as the Mach number increases. Therefore, for all practical purposes, as Mach number becomes large, H naught approximately is represented by the UE square by 2 term. Coming to the surface temperature or surface enthalpy, although it gets hot as the vehicle speeds increase, it has to be maintained at a much lower temperature using a suitable cooling technique nevertheless, so that the surface does not get melted or decomposed. So, if you have a coating on the surface which may be ablating or which you are keeping cool by using some surface cooling technique, then you are basically talking about this fact that HW is much lower than H naught. Put together, the expression for QW therefore would simplify. How would it simplify? Well, this part remains intact, but you have a much simplified representation for the enthalpy difference, which can approximately be represented as UE square by 2. So, as far as engineering estimates are concerned, this is perfectly okay, especially when Mach number becomes large, and therefore, we have a relation like this where we see that the QW depends on the cube of UE. Thus, aerodynamic heating at high Mach numbers increases with the cube of the velocity, and therefore, it would increase very rapidly as the Mach number increases. What about the aerodynamic drag? By definition, it is dependent on the square of the velocity, because that is the dynamic pressure part where the square of the velocity is connected, and therefore, the drag would increase as the square of the velocity. From the above estimates, it is evident that aerodynamic heating increases much more rapidly as velocity of the free stream increases compared to the drag. So, aerodynamic heating thereby becomes the dominant aspect of hypersonic vehicle design, not the drag. If we consider a hypersonic vehicle, let us say, which is taking off from an existing runway, and we expect it to accelerate through the atmosphere and reach orbit, the major aerodynamic heating that it encounters is during its ascent rather than during its entry. It has to accelerate, and quite a good part of that acceleration is in that part of the atmosphere which is at lower altitudes, and there the aerodynamic heating will be really severe. If it has to accelerate significantly within the sensible atmosphere using air breathing propulsion, this is more important, because it has to have the air at reasonably higher densities, and then high velocities will be combined with relatively high rho infinity, and they would collectively produce very high heating values going by this relation, where you see that this velocity clubbed with a reasonably high rho will create havoc. On the other hand, when the same vehicle comes for an atmospheric entry back from orbit and it follows a gliding path, we will discuss more of this in a later lecture. The trans-atmospheric vehicle, it will decelerate to lower velocities at higher altitudes. So, most of the deceleration occurs in that part of the atmosphere where it is less dense, and this basically leads to lower heating rates during descent than this vehicle would encounter during ascent. So, that was a discussion on aerodynamic heating based on some of the engineering intuitions. Before we close, we look at the laminar boundary layer at a stagnation point, which is of enormous significance for blunt bodies. So, here is a surface that you can see which enables stagnation point flow. So, here is a high Mach number flow approaching this blunt surface, and we have shown some of the details. One is the local surface radius of curvature at the stagnation point. So, this is basically the stagnation point where when the flow reaches, it comes to a halt. So, there is a particular streamline which is called as the stagnation streamline. The other streamlines get bent, few of them move upwards, few move downwards, a large number of them actually, and then there is a formation of the boundary layer, as you can see with the dashed lines. So, here is the boundary layer thickness near the stagnation point, and there is a running coordinate x here following the surface, and this is the velocity at the edge of the boundary layer. Now, if you go back to the ODEs for the compressible boundary layer, for stagnation point flow, we can show that they reduce to forms like this when we have a 2D geometry, typically like a cylinder. That means we are talking about a geometry like this, which is encountering this flow, and this is basically a 2D flow because it does not have any span wise variation. Then the QW comes out to be a form of this kind, where take note of this coefficient 0.57. There is a functional form following it which is dependent on Prandtl number, the rho e mu e product under root velocity gradient d u e dx, the u e being the velocity at the edge of the boundary layer here as shown, and then the difference between adiabatic wall and isothermal wall enthalpy levels. Now, instead of a 2D geometry, if you now consider an axisymmetric body, so about this axis you have a geometry like this. So, in this case we are considering a sphere facing the same flow. Of course, there will be shock, but behind the shock we look at the boundary layer flow, and near the stagnation point the boundary layer equations will look like this, which are somewhat similar to the 2D form we saw in the previous slide. You look at it carefully later on and you will see the difference. And these equations again they produce self similar solutions because they do not have any dependence on xi. In the axisymmetric problem, the coefficient turns out to be 0.763, which in comparison with the previous solution is higher. Here it was 0.57. So, trying to explain that, if we compare the QW expressions for cylinder and sphere, the only difference lies in the leading coefficient. The coefficient is higher for a sphere compared to a 2D cylinder, and this is due to what we call as the 3D relieving effect. So, in a 2D flow the gas has only two directions to move. When it encounters the body, it can move up or down, whereas in an axisymmetric flow the gas has three directions to move. It can move sideways in addition to up and down. So, going back here you have flow possible along an additional dimension in the case of a sphere. This produces a relieving effect on the flow, and consequently the boundary layer thickness reduces, which would enhance the temperature gradient at the wall, and consequently the Q dot or the QW will increase. So, this is a very important point which we need to take note of. Another very important point is that the velocity gradient term that we see in the QW expression has an inverse relation with the radius of curvature at the stagnation point, which means ultimately QW will depend on R, but that dependence, because here it is under root, therefore, we will have a dependence of QW in the inverse proportional to R. This is a very important result. It states that stagnation point heating varies inversely with the square root of the nose radius. We have missed a square root here. Hence, to reduce the heating, increase the nose radius. So, instead of making it as a small one, you make it more blunt. Here it is a small radius, here it is a larger one. So, we are talking about creating a larger radius so that the QW can be reduced. So, here the QW1 and the QW2, how do they compare? The 1 will be higher than the 2. To conclude, in this chapter we studied about velocity and temperature distribution within laminar compressible boundary layer over a flat plate for both adiabatic and isothermal walls. The boundary layer thickness rapidly increases with increasing free stream Mach number and decreases with wall cooling. Aerodynamic heating is in general much higher for adiabatic walls compared to isothermal walls. Aerodynamic heating approximately scales with the cube of the free stream velocity, while drag scales with the square of the velocity, and 3D relieving effect plays a very important role in stagnation point flow, and we compared between a 2D cylinder and a sphere. Thank you.